Hello, here we are for my second video on the introduction to plate tectonics. In this video, I plan to talk to you about the geography of the Earth, its layers, and topography. Are you ready to begin? Let's do so. I have some learning goals for this video, and they are that first of all, that you learn what the compositional layers of the Earth are. We'll also have to talk about material properties. This figures into plate tectonics, and the material properties that all materials exhibit are elastic, brittle, and ductile behavior. And finally, I want to tell you about the distinct mechanical layers that the Earth has and how that impacts the isostatic balance of the Earth's surface. We'll get to that by the end of the video. So in the first category, Earth is compositionally layered. You need to know the geography of the layers and something about their composition. You also need to know that the crust, the thing that we live on, is basically a chemical differentiate of the mantle. We make the crust out of taking some of the chemicals in the mantle through the process of volcanism and making a crust. This process leads to a bimodal distribution of crust on Earth. There is the crust that underlies the ocean and the crust that underlies the continents. On the elastic, brittle, ductile portion of this video, the main takeaway is that at high temperature, all materials exhibit increased ductility. The two mechanical layers that you need to know about by the end of this video are that there is an asthenosphere and a lithosphere. Lithosphere is the fancy way of saying plate in plate tectonics. Okay, let's jump right into the compositional layers. There's the Earth. It has a radius of, on average, 6,371 kilometers. At the very center of the Earth is an inner core, which is solid. It's about 1,200 kilometers in radius. Surrounding that is the outer core of fluid metal with a radius of about 3,400 kilometers. The inner and outer core are dominated by iron, but they also have about 10% mixture of most of the elements of the periodic table. The mean density of the core is about 12.4 grams per cc. Remember, water has a density of 1, so the core is over 12 times denser than water at ambient conditions. Now, iron itself has a density a little less than 8 grams per cc, so what's happened at the center of the Earth is the compression of all the overlying mass has increased the density of the material until it's some 50% denser than iron under ambient conditions. Surrounding the core is the mantle, shaded in green here. Now, the mantle has a mean density of 4.1 grams per cc, which is denser than most surface silicate rocks, but in fact that's again a result of the high pressure causing a compression of the minerals, both to self-compression as well as change of crystal arrangement. Now, the mantle is about half the radius of the Earth, but it's the larger volume than the core, and the mantle makes up about 67%, 2/3 of the mass of the Earth. On the very top is the crust, and in this drawing the crust is too thin to show up. It is only 5 to 70 kilometers thick, and 70 is a very unusual number. Most of the crust is much thinner than 70. The crust, being so thin, accounts for a very small amount of the Earth's total mass, less than 0.5%. The mean crustal density is somewhere around 2.8 grams per cc. Now, the radius of the Earth at the equator is about 21 kilometers greater than the radius of the Earth at the poles. Thus, the Earth has an ellipsoidal shape stretched out at the equator and squashed at the pole. That stretched out shape is a result of rotational forces acting on ductile materials, the Earth's mantle. And we'll get to that in a moment to talk about ductility. Let's talk first, though, about the composition of the layers. The Earth's mantle. Well, the Earth's mantle is primarily a magnesium iron silicate mixture. Magnesium iron silicon plus oxygen. That's pretty simple. 3 elements, magnesium iron silicon plus oxygen. Then beyond that, there's a few percent aluminum and calcium, and beyond that there's sub-fractional percents of all the other elements in the periodic table. So the very uppermost mantle is a mixture of common minerals, about 60% olivine, about 30% pyroxenes, and about 10% other things, including garnets. The density of the mantle at the top is less than the average density of the mantle. It's about 3.2 grams per cc. Below 400 kilometers, there are additional transitions of the silicate minerals to high-pressure phases, which have higher densities, and that gives rise to an average density for the mantle that's greater than the upper mantle. So let me take you on a quick tour with some pictures. Here's a piece of the upper mantle. This was extracted from the walls of a volcanic conduit about 60 kilometers down, ripped off and carried to the surface. There's what the mantle looks like. It's a greenish rock. You focus in on it, you can see it has minerals of olivine and mineral pyroxene, olivine dominating over the pyroxenes. The Earth's crust. Let's talk about that. The Earth's crust is enriched relative to the mantle in elements of silicon, aluminum, potassium, sodium, and calcium, light elements relative to the iron and magnesium. There are some dominant minerals in the crust, and they're quartz, amphiboles, and feldspars. And the crust is bimodal. There are 2 kinds of typical crust. There's the oceanic crust, the crust that underlies the ocean, which is thin. It's only 5 to 7 kilometers thick. A major rock type for the oceanic crust is basalt. The density of that's about 2.9 grams per cc. Then there's the continental crust, much more heterogeneous than the oceanic crust. Continental crust is on average 35 kilometers thick, but in fact, under some areas, for instance, the Tibetan Plateau, it gets up to 70 kilometers in thickness. The continental crust is more silica-rich than the oceanic crust. That leads to a lower density. It's 2.7 on average. So Earth's crust. How did we get it? You produce crust by differentiating the mantle. Chemical fractionation associated with partial melting the mantle. The idea is that a magma, a melt derived from a rock, is chemically different than the rock. So the magma preferentially takes some of the chemicals out of the rock and carries them off. So first step in the process, partial melt the mantle, and the rock type that you get is basalt. So the magma melting in the mantle is basaltic. Then a further fractionation, partial crystallization of the basalt, further processing in the presence of water and other crustal rocks leads to rock types that are generically called granites. Let's look at this picture here. Up there, that's a picture of basalt flows. It's a ubiquitous rock type. You can go all over the world and see basalt. Basalt, when it flows out on the Earth's surface, typically cools and has the columnar structures that you see here. A felsic rock, a rock fractionated from basalt that is very typical on Earth, is shown here as granodiorite. It's a rock more rich in quartz and feldspar. We blow it up, and there you can see the more transparent crystals in the rock are the quartz. The more milky colored are the feldspars, and then the darker minerals in this rock are biotite. So, takeaway message: the crust is enriched in elements other than iron and magnesium, the elements that dominate the mantle. The crust is a melt, partial melt of the mantle that is lower density than the mantle. So it's the froth that rises to the top of the convecting mantle system. Okay, we've covered the compositional layers. Let's talk about mechanical layering of the Earth. And this has to be a distinct idea in your mind from compositional layers. Let's consider properties of materials. And the properties that I want to talk about are elastic, brittle, and ductile behavior. I brought along my trusty yardstick to demonstrate elastic and brittle behavior. Elastic behavior involves applying a force, there I've applied a force, and causing a material to deform. See, it's arced here. This is a strong ruler. Okay, it's deformed, but when I remove the force, it returns to its initial shape. So an elastic response of a material is to deform under the presence of stresses, but return to an undeformed state in the absence of stresses. Now, every material has elastic behavior, including rocks. Now, you can't deform a rock this much, but you can deform it a little elastically, and then it would return to its initial state. All materials exhibit another behavior if they are stressed and strained too much. So if I deform it too much, I snap it. That's the brittle behavior. Now, this elastic ruler allowed me to bend it a whole lot before it broke. Rock would not strain so far before it broke, but again, it would break as in brittle fashion like that. Okay, so now let's turn to ductile behavior. Well, here's a iron rod. It also is elastic. I can flex it a little bit, and you can't really see it on the video, but it flexes and returns to its initial shape. However, this one, if I flex it too far, instead of snapping like the ruler, it will simply ductily deform and be permanently bent. So, ductile behavior involves applying a stress, straining a material, and then when the stress is removed, the material remains strained. Okay, remember, elastic, brittle, ductile, all materials exhibit elastic, brittle, ductile behavior, but they exhibit different amounts of elastic, ductile, brittle behavior depending on what they're made of and depending on environmental conditions. So, at low temperature, materials tend to be rigid and elastic. If they break brittle in a brittle fashion if they are overstressed. At high temperatures, however, solid materials have increased ductility. This is why a blacksmith puts the horseshoe in the forge before trying to bend it to shape it to the shape of the horse's foot. You artificially heat it, deform it, cool it, and then it's permanently deformed in the shape that you want. Rocks, too, can be deformed at high temperature without breaking. So at low temperature, they can break when stressed. At high temperature, they can flow, even though they are not melted. So ductility is an ability to deform without breaking. And hot solids flow, they deform without being melted. So typically materials can be elastic for short-term stresses, but if the stresses are maintained for long periods of time, they can begin to deform. Now let's talk about Earth's mechanical layers. The lithosphere is the cold outer layer of the Earth. Because it's cold, it is in the elastic, brittle regime of material behavior, so it behaves rigidly, but when it breaks, it breaks in a brittle fashion. So that's the lithosphere. The lithosphere includes two compositional layers. It includes the crust, and it includes part of the upper mantle, and that part of the upper mantle, which is below approximately a temperature of 1300 degrees centigrade. So mantle rock, primarily olivine, is pretty rigid as long as its temperature is below 1300 degrees centigrade. So lithosphere is the plate in plate tectonics. Now below the lithosphere, the mantle is warmer, and in this regime, it has enhanced ductility so that it is able to flow under the influence of applied stresses. So we call the portion of the mantle that deforms under stress to be the asthenosphere, and the portion of the mantle that is rigid and breaks brittly is the lithosphere. So the asthenosphere is the convecting region of the Earth's mantle, and we'll come back to that in a minute. So I've brought this in as a fancy animation for a reason. Note, compositional layers are not the same as mechanical layers. I don't know how many times students and even professionals will refer to the Earth's crust when they really mean the Earth's lithosphere. Do not confuse crust and lithosphere. Lithosphere is the crust plus the mantle. It's more mantle than crust. As we'll see in a minute, the crust is simply a thin veneer sitting on top of a much thicker mantle lithosphere. Shall I play that animation again? So play that over on your mind as you review this topic. Okay, let's talk about asthenosphere, lithosphere structure of the Earth. The lithosphere boundary is controlled by temperature. It's gradational. There's not a single point that you can put your finger on and say, above here it's lithosphere, below here it's asthenosphere. But there's some regime going through a temperature range near 1300 degrees where the mantle rock is less ductile to where it is increasingly ductile. So the mantle lithosphere is deeper where the mantle has chilled, and where the mantle is hottest, the lithospheric transition is the shallowest. Typically, the lithosphere thickens with distance as you move away from divergent boundaries. So farther you are from the boundary, the older the lithosphere is. The lithosphere forms at the spreading center. It has zero thickness there, and it simply gets thicker as the mantle cools and moves away from the spreading center. A nominal typical thickness for the lithosphere is about 100 kilometers. So as you get older and older, it gets thicker and thicker, but a nice reasonable number to keep in mind is 100 kilometers. So we're going to turn to isostatic equilibrium. A consequence of the mantle having ductile behavior is that the Earth's surface tends to be in isostatic equilibrium. So what does that mean? Well, I've put water here. Water has a density of 1 gram per cc. Now, you all know that buoyant bodies rise to their own level when placed in water. So imagine putting a block of ice on top of the water here. The ice will sink into the water until it finds its level. The ice is less dense than the water, so it does float. The ice has a density about 10% less than the density of water. So if I draw a reference line across here, about 10% of the ice sticks above the water, and about 90% of the ice is below the water level. I call this part above little h and big H for the part below. We can turn to Archimedes, who first articulated the idea, and the principle of how things float is very simple. If you take a column through any point here, a vertical column, it will contain the same mass. So if I construct a column of unit area through the ice, there's the portion that's above the water level that has a mass of its density times its height. And then there's the column below the water level, which is, again, the capital H times the density of ice. Now, a column of water on the side, illustrated in yellow here, has total mass of density times capital H. So that if we set this up as a chemical formula, you can say that the density of water times H has to be equal to the density of ice times the total thickness of ice. That can be rewritten as this formula, which says the height above water is equal to the fractional difference in density between ice and water times the amount of ice below the water level. Very simple for ice and water, and it's equally simple for crust and mantle. So if we replace the ice with a crust, which has a density, continental crust of around 2.7 grams per cc, and we replace the water with mantle that has a density of about 3.2, you see there's a 0.5 gram per cc difference in density. The crust can actually float in the mantle as long as the mantle ductily deforms under the load given by the crust. So we just replace the formula here. The height sticking above the mantle level is going to be the fractional difference between the crust and mantle times the height of the thickness of the crust that sticks below the mantle level. And using that formula, you'd find that about 18% of the crust sticks above the mantle level. So let's look at Earth topography. Let's define a mantle level as there, and let's put a piece of crust on the mantle. Now, I've introduced the crust sitting too high, and it will simply sink into the mantle. The mantle deforms and flows away as the crust pushes down until the crust finds its point of equilibrium. Continental crust is thick, 35 kilometers, and so you have a picture like this. Now, the oceanic crust is much thinner, 5 kilometers, and it's also denser, 2.9 grams per cc. So it sinks into the mantle to find its own level. It doesn't stick as far above the mantle, nor does it stick as far down into the mantle. The combination of being thinner and denser means it rides lower in the water, or in the mantle in this case. Now finally, if I step over here and put in another chunk of continental crust, you see we have a basin between the two crustal sections. That basin can conveniently be filled with water to form an ocean, and thus we have water overlying oceanic crust and land in regions of continental crust. In fact, now if you look at a color-shaded map of the world, you can see it's basically two colors. There's the blues of the ocean depths and red of the continental areas. Very little of the Earth's surface is right at sea level. Most of it's either above sea level at some point, represented by an average thickness of continental crust of 35 kilometers, and the other part of it is below sea level by amount, represented by the thickness and isostatic equilibrium of the oceanic crust. I can turn that into a quantitative plot, and what I have here is a line with the horizontal axis being elevations going from 10 kilometers below sea level to 10 kilometers above sea level. Now Mount Everest is over there on the far right of this graph. It's at an elevation of 8 kilometers above sea level. In contrast, the Marianas Trench is about 11 kilometers below sea level, and it is at the extreme of this scale. So sea level in here, axes now in the vertical axis, we're going to use percents of the surface area. The oceanic regions extend from sea level down, and you notice that as it gets to the depths of the Marianas Trench at 11 kilometers, very little of the Earth's surface is that deep. But you'll notice it comes up to a peak of a little less than 20% of the Earth's surface at a depth of about 5 kilometers below sea level. Continental areas, on the other hand, form a second peak, represented by average thickness of 35 kilometers of the crust. And you can see again it tapering off to very little area on the Earth's surface that is as high as 8 kilometers above sea level. So the mean ocean depth is 5 kilometers below sea level, and the mean continental elevation is about 800 meters above sea level. This bimodal distribution is a direct response to isostatic equilibrium given two flavors of crust, a basaltic crust underlying the ocean and a more granitic crust underlying the continents. So that ends my lecture on layers and topography. Coming up next, I'll talk about plate boundaries and the processes.